Hello and welcome to the webinar Traditional and Modern Colour Theory, brought to you by the Colour Society of Australia's New South Wales Division. The Colour Society of Australia is the Australian affiliate of the AIC, or International Colour Association, and is a network of designers, colour consultants, artists, scientists, students and teachers who hold regular events and conferences throughout Australia aimed at continuing education in all facets of colour. For more information and events, please see our website and Facebook page. My name is David Briggs, and this webinar is based on 2 pages I recently added to my website on colour theory for painters, The Dimensions of Colour. Colour training in the arts today is curiously divided between traditional and modern colour theory. Traditional colour theory characteristically begins with the concept of 3 primary colours identified as red, yellow and blue, as for example here in Johannes Itten's 1961 book, The Art of Colour. These historical primaries rose to prominence over the course of the 17th century, and then as now were based on the observation that mixtures of a wide range of colours can be obtained from colorants, paints and dyes, of just a reddish, a yellowish and a bluish colour, together with the psychological perception that red, yellow and blue seem pure or simple compared to most other colours. A second characteristic of traditional colour theory, in its typical form, is that it speaks as if colours themselves intermix when we mix colorants, so that the colour of a paint mixture is made of the colours of its component paints. From this viewpoint, each of the 3 secondary colours made by mixing colorants of 2 primary colours is made of those 2 colours. For example, green is made of the colours yellow and blue. Black, grey and greyish colours are commonly held to contain all 3 primaries, since they can be made by mixing a secondary with the remaining primary, which is called its opposite or complementary colour. Greyish colours are sometimes called tertiary to reflect this belief that they are made of 3 components, although this term is also used in traditional colour theory in a different sense for the 6 third-order colours that lie between adjacent primaries and secondaries, and so are supposed to contain 2 primaries in unequal amounts. By extrapolation, red, yellow and blue, along with white and sometimes black, are deemed to be the fundamental components of all colours, and paints of these 3 colours should, in theory, yield all possible colours by intermixture. The fact that they do not can be blamed on a lack of pure primaries among available paints, and clearly a bluish-red paint like magenta, which by this view contains the primary colour red plus a visible impurity of blue, must be further from being a good colorant mixing primary than one that is perceptually pure red. Traditional colour theory readily took up Newton's concept of a circle of hues, introduced in this diagram from his Optics of 1704, in the form of the artist's colour wheel with its symmetrically placed red, yellow and blue primaries. For example, in this diagram from an anonymous treatise on miniature painting published just a few years later in 1708, and in this 1835 example by the chemist George Field. Field believed that red, yellow and blue would balance perfectly if present in the proportions 5:3:8, and the small numbers in the inner circle here show the ratios in which various mixed colours would need to be present in order to maintain this balanced ratio. Johannes Itten expressed a very similar idea under the heading of contrasts of extension, using a slightly different ratio that he mistakenly attributed to Goethe, but which actually comes from Schopenhauer. More problematic for traditional colour theory was Newton's conclusion that lights of all colours are composed of rays of the innumerable but 7 named colours of the spectrum, and that green and orange lights could be physically compound but could also be physically simple. This problem, however, could be countered by supposing that the spectrum is not continuous, as Newton had thought, but is actually made of separate red, yellow and blue rays that produce the remaining colours by intermixture. The theory that our eyes have 3 kinds of receptors responsible for colour vision was first suggested based on this idea of red, yellow and blue rays. In this enviably simple view of colour, The Colourant-mixing primaries coincide with the primaries for mixing coloured lights, with the sensitivities of the visual receptors, and with the psychological primaries of our colour perception. For example, here a mixture of yellow and blue paints reflects only the yellow and blue rays, which are detected by the yellow and blue receptors in the eye, leading to a mixed sensation of green. The three-ray hypothesis was quite widely accepted in science in the 18th and early 19th centuries, and the first three-dimensional systems for classifying object colours were based on the belief that all such colours are mixtures of red, yellow, blue and white, plus or minus black components in various proportions. On the left we see a three-dimensional colour space proposed in a 1758 lecture by the Swedish astronomer Tobias Meyer, in which colours are arranged in a double pyramid according to the proportions of red, yellow, blue, black and white components. In the example on the right, the three primaries are assumed to mix to make black, so that only white needs to be added. The three-ray hypothesis was not finally overturned until 1852, when the version of it promoted by the Scottish physicist Sir David Brewster was convincingly demolished by the brilliant German physicist and physiologist Hermann von Helmholtz. In subsequent years, Helmholtz, his contemporaries including James Clerk Maxwell and Ostwald Hering, and their successors, collectively transformed our understanding of what colour is and how it works as fundamentally as Darwin transformed our understanding of biology over the same period. And this new understanding in turn led to modern colour printing, colour photography, cinema and television, and eventually to digital photography, painting and rendering. Modern colour theory, as understood on my website, is a system of practical guidance resting on the legacy of this late 19th century revolution, adapted to the practical needs of painters and teachers of painting. In line with Hering's widely accepted opponent model, modern colour theory recognises four psychological primaries, the three historical primaries plus green, arranged in two opposing pairs, yellow versus blue and red versus green. This model is founded not on neuroscience, but on contemplating how we experience colour. Only red, yellow, green and blue are experienced as pure hues, and all other hue perceptions are combinations of adjacent pairs of these four. Yellow-red, orange and scarlet, yellow-green, blue-green, cyan, turquoise, etc., and blue-red, purple, magenta, and so on. Red, yellow, green and blue are thus the true primary colours of modern colour theory, as opposed to primary colour stimuli of additive mixing or primary colorant hues of subtractive mixing. These four opponent hues are not physical components of light, but are perceptions created in the brain of the observer in the form of yellow versus blue and red versus green colour opponent signals. Blue is evoked by the shorter and yellow by the longer wavelengths of visible light, while green is evoked by the middle wavelengths and red by the two extremes. Thus the colour red, for example, is not something that exists outside us, but is a tag that is applied to the two bands of wavelengths that have nothing in common apart from being at the two ends of the range visible to humans. Successive combinations of these four hue perceptions create the sequence of hues seen in the spectrum, as well as the non-spectral hues like magenta, and thus explain how we arrive at this circular succession of hues that has no physical basis in the linear sequence of wavelengths of the spectrum. The concept of four psychological primaries has strongly influenced several important colour order systems, notably the Ostwald System, which was the standard for British education in the 1930s. Here we see a British school textbook explaining the Ostwald System and a box of Ostwald System watercolours by Winsor and Newton. And the Swedish Natural Colour System, or NCS, which is the current colour standard in Scandinavia and Spain. The idea of opponency was also foreshadowed in historical and traditional texts, including the writings of Leonardo, Goethe and others. In addition to the four psychological primaries, modern colour theory refers to three additive or light mixing and three subtractive or Colourant-mixing primary colours, for the colours of lights and colorants respectively that yield a maximum gamut or range of colours of their mixtures. None of the optimal additive or subtractive primaries bear an exact relationship to any of the psychological primaries, but we have a strong unconscious predisposition to apply to the former the names of these hues that form the framework of our experience of colour. Thus before the 20th century, when our best available Colourant-mixing primaries were slightly greenish-yellow, bluish-red and greenish-blue paints, we almost universally labelled these primaries simply as yellow, red and blue. In the same way today, we routinely label the orangish-red, yellowish-green and blue or violet-blue primaries of additive mixing technology as simply red, green and blue, as in RGB. I think that it's counterproductive to the wider acceptance of modern colour theory, as well as misleading, to dismiss the red, yellow and blue primaries as merely obsolete, or worse, to insist, by adopting an unrealistic definition of the term, that primary colours do not exist. The three historical primaries were as much a step towards recognition of the four modern psychological primaries as they were an imprecisely named set of Colourant-mixing primaries. So while the number 4 is the key to colour perception, 3 is the key to colour stimulus and colour technology. This number 3 stems from the fact that colour vision is ultimately based on 3 types of receptors in the eye called L, M and S cone cells. These cone cells are often loosely termed red, green and blue, and were once believed to detect the red, green and blue-violet bands of the spectrum, and to directly create red, green and violet or blue fundamental sensations respectively. However, it is now known that the L, M and S cones do not detect individual wavelength bands or colours of the spectrum, but respond to very broad and extensively overlapping ranges of wavelengths, peaking in the parts of the spectrum we see as greenish-yellow, green and blue-violet. And they respond in exactly the same way, just to different degrees, throughout their range. Nor do they directly create sensations of individual colours. Instead, differences in the responses of the 3 cone types are recorded in the retina in the form of cone opponent signals, L-M and L+M-S. Colour as such is created in the brain in the form of colour opponent signals based indirectly on the wavelength dominance information contained in these cone opponent signals. When a light creates a balanced response of all 3 cone types, the 2 cone opponent signals both balance at 0 and the light is seen as colourless, that is, white light. Colours of lights are perceptions created by our visual system in response to an uneven distribution of wavelengths, as detected by an unequal response of our 3 cone types. RGB red, green and blue lights work as additive light-mixing primaries because each of them stimulates one cone type more than the other 2, and so when mixed in different proportions, they produce a large variety of relative L, M and S cone responses, and therefore cone opponent signals, and therefore ultimately colours. Red and blue lights unsurprisingly yield mixtures passing through magenta, red-blue, and green and blue lights unsurprisingly yield mixtures passing through cyan, green-blue. But, to the perennial astonishment of students, red and green light mixtures pass through an apparently new colour, yellow, that is neither reddish nor greenish. This asymmetry is the inevitable consequence of the mismatch between having 3 additive and 4 psychological primaries. The yellow is not really a new colour, in that it is already present in the colours evoked by the component lights. They are orange-red and yellowish-green after all. And when these are mixed, the yellow signals add together, while the red and green signals cancel out, leaving pure yellow. The yellow colour is not made of the colours red and green, and is certainly not some sort of mistaken guess that the wavelength is between those of red and green. Helmholtz recognized that the color mixing of two colorants was in large part a subtractive process in which the color of the mixture depends on which wavelengths both colorants pass on. It was soon realized that in theory, three transparent colorants that each completely absorb one additive primary and completely pass on the other two would, when mixed subtractively in various proportions, yield the entire gamut of those additive primaries and hence be optimal for subtractive mixing. These ideal subtractive primaries would therefore resemble the pure yellow, red plus green, magenta, red plus blue, and cyan, blue plus green, colours of the digital hue circle, the last two being far from the red and blue primaries of traditional colour theory. It took many decades, however, before permanent pigments at all close to ideal magenta and cyan were developed, and even today our best magenta and cyan paints and inks are redder and bluer respectively than ideal subtractive magenta and cyan. This figure shows the calculated mixing paths and reflectance profiles of some actual cyan, magenta and yellow paints, plotted using the program Drop to Colour by Zsolt Kovacs-Vajna. As we'll see in a later diagram, these paints produce a larger and more evenly distributed gamut or range of colours than the historical red, yellow and blue primaries. Note well in figure B that in subtractive mixing, yellow and cyan colorants make green not because green contains yellow and cyan, as typical traditional colour theory assumes, but because both yellow and cyan colorants pass on large amounts of green wavelengths. Just as different sets of colours are considered primary for perception, for mixing lights and for mixing colorants, modern colour theory also recognises somewhat different pairs of opposite colours in these three contexts. For every imbalance of cone responses that we experience as a colour of light, there are lights that create an opposite or complementary imbalance, and which therefore can create white light if added in the right proportion. Examples of such pairs of lights include the RGB red-cyan, green-magenta and blue-yellow pairs familiar from graphics programs. Perhaps because the relationship between cone opponent responses and the colour opponent signals we ultimately experience is indirect, pairs of colours that mix to make white light, additive complementaries, do not always coincide with the axes of our perceptual framework of opponent colours, as determined by experimental studies of large numbers of observers. In this CIE XYY or chromaticity diagram, additive complementaries are connected by a straight line through the central white point. Middle yellow and middle blue are essentially complementary, but middle red and middle green are not. Colours of pairs of colorants that make a neutral, meaning black or grey mixture, are called subtractive or colorant-mixing complementaries. The result of subtractive mixing depends on the precise wavelength by wavelength absorption of the colorants involved, and cannot be predicted exactly from their colours alone. But the importance of this proviso is sometimes exaggerated as far as actual colorants go, and it does not prevent reasonably reliable generalizations being made about colorant-mixing complementaries. Subtractive and additive complementaries coincide quite closely near the red-cyan and green-magenta axes, but differ substantially near the yellow-blue axis. A yellow and a blue paint that are opposite on this Munsell hue circle would be approximate additive complementaries, so that when lights from these paints are mixed, for example using spinning discs, they would make a near neutral. But such paints nevertheless reflect enough green wavelengths in common to make a mid-chroma green when mixed physically. It is this generation of green as an apparent compound of two visually distinct colours that has influenced painters since Leonardo to reject or question green as a simple or primary colour. To make a mixing complementary for yellow paint generally requires a precisely balanced mixture of blue and violet paints that is more reddish than the blue additive complementary, but less reddish than the middle purple expected from traditional colour theory. I think it's worth noting that after-image complementaries show a similar sort of pattern to these paint mixing complementaries, in that they agree well with the additive complementaries near the red cyan and green magenta axes, but depart in a similar way near the yellow-blue axis. Complementary coloured afterimages result from local changes in the relative adaptation of the three cone types, and seem to act as virtual coloured filters, subtractively modifying the areas of the visual field that they occupy. Modern colour theory, like modern colour science, makes constant practical use of concepts of three-dimensional colour space. The framework of hue, value, that is lightness, and chroma, or colour strength, devised by the American artist and art teacher Albert Munsell for classifying object colours, has proved especially useful for painters. Munsell explained his system in his small book A Colour Notation in 1905, and embodied it in a published atlas of colour samples in 1915. The atlas was succeeded by the Munsell Book of Colour, published from 1929 to the present, and following extensive testing and refinement by the Optical Society of America in 1943, has become a very widely accepted standard in science and industry. The Munsell Book of Colour, or any of several less expensive alternatives, enables a painter to examine almost every colour obtainable from paint mixtures, set out in a logical, value-based arrangement. The system makes a potent conceptual framework for observing colours, for understanding colour mixing in paints, and for creating effects of light from the imagination. While painters most commonly use only the framework of relative hue, value and chroma rather than the absolute Munsell dimensions, there are strong practical benefits to at least using an absolute scale of value like the Munsell scale. A simpler system of hue, value and relative chroma devised by Munsell's friend and rival Denman Ross was also widely used in art education. Ross's value scale of black and white plus 7 greys obtained by interpolation, high light, light, low light, etc., is still encountered today. The figure bottom right shows Ross's subdivision of 12 hue planes according to what Ross called intensity, that is, chroma relative to the absolute maximum possible for that hue, and what Ross called neutralization, that is, chroma relative to the maximum possible for that hue at that value. Ross's system was further developed as a colour space by his former student Arthur Pope. As seen in the figure on the lower right, Pope shows how Ross's hue planes could also be subdivided according to the relative purity or saturation and relative brilliance or energy of vibration of the reflected light producing each colour. A conceptually similar subdivision was later adopted as the HSB or HSV colour space of graphics programs. Lines of uniform saturation are of great importance to the painter in that they correspond to shading series, or the paths of image colours needed to represent an object of one colour under different levels of illumination. Colour spaces such as the historical Ostwald System and the modern Natural Colour System or NCS that lack a dimension of grayscale value are less useful for most painters, but have found favour in many areas of design. The top centre diagram here shows a cross-section of the Ostwald System, displaying divisions of the hue planes according to relative black, white and colour content. The series of colour spaces devised by the Commission Internationale de l'Éclairage, or CIE, are central to modern colour science and to the development of all forms of digital colour technology, including digital painting. Most fundamental is CIE XYZ space, which is the foundation of colour management, and measures colours in relation to 3 device-independent virtual primaries that are not colours, but are purely mathematical transformations of actual lights. More commonly encountered by digital painters might be the CIE XYY or chromaticity diagram and CIE LAB space, which arranges colours similarly to the Munsell system, but describes their position in terms of reddish versus greenish and yellowish versus bluish chroma, instead of hue and total chroma. Digital painters can select and apply modifications to their colours using a great variety of colour spaces for different purposes, though probably only a small minority understand these spaces well enough to take full advantage of this versatility. Here we see some of these spaces. There's RGB space, which is based on relative brightness scales of the red, green and blue component lights, and its inverse ideal CMY space. HLS space, which is a simple double cone model using digital hue, a pseudo value dimension called L, and a measure of relative chroma called S. HSB or HSV, based on digital hue angle, measures of saturation S and brightness relative to the maximum possible for that hue and saturation B. YCBCR, which is used in JPEG compression and is a space for some operations in Photoshop. An F and G, a version of CIE LAB space known as lab space, used as a means for designating colours in the colour picker and as a working colour space in Photoshop. Many painters who use traditional media are familiar with CIE colour spaces through the handprint website of Bruce McAvoy, whose plots of watercolour paints as points on the CIE LAB and CCAM02 hue planes are quite widely quoted on painting forums. Principles governing the relationship of colour and light have been an important part of artistic colour theory since the times of Alberti and especially Leonardo. But these principles could be expressed only verbally before modern models of colour space provided a framework for their more precise formulation. In the early 1920s, Arthur Pope set out a series of important principles of colour appearance in terms of his own colour order system, and beginning in the 1930s, Faber Buren used the framework of the Ostwald and Munsell systems to describe colour relationships that create various effects of iridescence, lighting and atmosphere. The diagrams on the left here by Arthur Pope from 1921 conceptualise the effect of changing levels of illumination and of a greyish atmospheric mist on the appearance of an array of uniformly coloured stripes. On the right we see realisations in Photoshop of the relationships postulated by Pope. In the middle decades of the century, the American illustrator and highly influential teacher Frank Riley devised an extremely elaborate system for calculating effects of light and atmosphere within the framework of the Munsell system. Applying Riley's system in oil paints generally involved the use of an extensive palette of strings of premixed colours, like we see bottom right here, kept in tubes. Principles of this kind can now be applied very easily using the controls available in digital painting programs. For more on this, please see section 10, Principles of Colour, from my website, and of course can be applied automatically using 3D rendering software. Figure A and B here show emulation of additive mixing of coloured lights, A, and the effect of a translucent atmospheric mist, B, from the original upload of my website. Figure C shows a digital painting exercise in which students examine a photograph to determine lighting and atmosphere, and then paint in the simple object to be consistent with these. Numerous excellent texts explaining modern colour theory for artists began to appear very soon after the Helmholtz-Maxwell revolution, and those by Benson, Bezold, Rood and Church in particular proved popular enough to be reissued in multiple editions over several decades. One of the most influential was Modern Chromatics, or the Student's Textbook of Colour, of 1879 by American physics professor and trained painter Ogden Rood, which is a revelation as to the level of technical understanding of colour and light that was considered appropriate for academically trained artists of this time. It's difficult to say just how widely painters of this era used modern colour theory, because most art historians seem to neglect fundamental elements of the artist's craft like colour in the pursuit of more esoteric concerns. For example, author Richard Kendall maintained that there is no indication that Degas joined those of his contemporaries who engaged in a more thorough study of colour theory and application. On the contrary, a previously unpublished and rather inaccurate drawing of an elementary colour wheel from one of Degas' notebooks of the early 1880s suggests a delayed interest in such matters." End quote. The drawing is not an inaccurate elementary colour wheel, but in fact shows the recently established additive complementaries, probably transcribed from Rude's Modern Chromatics, whose French edition had been published in 1881. Thus the painter Degas took an interest in the latest developments of modern colour theory, even though the art historian and Degas specialist, Richard Kendall, did not. The pioneering early 19th century texts were followed over the course of the 20th century by numerous others incorporating various aspects of our developing understanding of colour, by Albert Munsell, Wilhelm Ostwald, Arthur Pope, Faber Biren, and many others. The Munsell system was disseminated throughout the 20th century in numerous editions and reprintings of Munsell's A Colour Notation, and in its successor, the new Munsell Student Colour Set of 1994 by Joy Turner Luke. Through college textbooks such as Maitland Graves' The Art of Colour and Design, and orally through teachers such as Frank Riley and his various disciples. Although Riley did not publish his Munsell-based painting system himself, elements of it have been published by several of his former students, most completely by Apollo Dorian. A simple introduction to many elements of modern colour theory is included in James Gurney's excellent Colour and Light, A Guide to the Realist Painter, which I recommend as a first step to any students who have a difficulty approaching my own site. For more detailed accounts of colour science written for artists and of historical and modern colour order systems, the best and most reliable sources are the books of Professor Rolf Querney, while Bruce McAvoy has presented a wealth of information on advanced topics on his enormous handprint website. Although textbooks for academically trained artists ably explained modern colour theory from its beginnings, traditional colour theory persisted into the 20th century in other texts, especially those written for amateur painters, and in the thinking of other artists, notably some of the pioneers of abstraction, Kandinsky and Mondrian for example, and Expressionism. Throughout the first half of the century, fully modern and fully traditional colour theory texts coexisted, and many texts presented both approaches. Since the 1960s and 70s, however, traditional colour theory has had a renewed and dominant influence on art education, even at tertiary level, very largely in the form set down in Johannes Itten's book, The Art of Colour, in 1961. Itten's book has been so influential that it defines the limits of artistic colour theory for the majority of sources on the internet today. A symmetrical traditional colour wheel, schemes of supposedly objective colour harmony, dictionary meanings of colours, the limited subset of colour phenomena known to early 19th century science, and very little on colour in relation to the representation of light and atmosphere. Traditional colour theory has entered the digital realm in the form of apps like the widely used Adobe Color CC, formerly Cooler, which calculates complementary and triadic colour sets using a modified digital hue circle in which the hue angles are intended to conform to the traditional colour wheel. As a result of its half-century of ascendancy, many artists today assume that traditional colour theory has dominated art education continuously since its origins, and assume modern colour theory is a very recent intrusion. Itten took many elements of his colour theory from that of his teacher Adolf Hölzel, but in his book of 1961 he eliminated almost all of the elements that Hölzel had derived from late 19th and early 20th century science, and presented a version of traditional colour theory and classification almost entirely fixated at an early 19th century stage of development. Itten's colour star lithograph of 1921, for example, which he had used as the basis of his teaching at the Bauhaus, follows Hölzel's 12-hue system derived from the scientist Wilhelm von Bezold, and places yellow, cyan blue, and a purple or magenta at evenly spaced intervals. but in the art of colour, Itten reverted to a completely traditional circle with evenly spaced red, yellow and blue primaries, secondaries and 6 intermediates. Itten's 3 primary colours are defined in his text as perceptually pure hues, oddly enough in terms of the names of the 4 psychological primaries of modern science, which otherwise escape mention. A red that is neither bluish nor yellowish, a yellow that is neither greenish nor reddish, and a blue that is neither greenish nor reddish. Secondary colours are said to contain 2 primaries and must not lean towards either of their components, and these secondaries are held to be complementary to the remaining primary in paint mixing, in additive mixing, in simultaneous contrast, as negative afterimages, and even in expressive interpretation. Thus, according to the logic of the system, primary or middle red must be complementary in all of these ways to a middle green that does not lean towards either yellow or blue. But as we've seen, the additive complementary of a middle red is bluish green rather than middle green, and the additive complementary of a middle green is a purplish red, and the very similar relationships apply to afterimage complements. Yet accurate complementaries, the colour that the eye demands after seeing another colour, are accorded enormous significance in Itten's theory as the basis of what he believed to be objective colour harmony, which in all its forms depends on a balance of complementary opposites. The next slide shows Itten's exemplars of middle red and middle green, as well as the reds and greens from the 48 online examples of traditional colour wheels shown previously. You can examine the afterimage complementaries of Itten's colours by focusing on the black dot between the coloured sectors for 5 or 10 seconds, and then shifting your gaze to the corresponding dot to the right. Most observers will see the afterimage of the red as a little more cyan, and the afterimage of the green as a little more magenta or pinkish than the supposed complementary. However, most of the online examples, including Adobe Color CC or Cooler, place the red-green pair close to the additive primaries called red and green, resulting in extremely inaccurate complementaries, as you can confirm by repeating the procedure for Figure B. Similar examination of any number of online examples will show how many people pass on traditional colour theory dogma without subjecting it to the simplest of checks. Itten does include 2 examples of modern colour theory on a single page entitled Colour Physics early in the book, but these are puzzling to reconcile with the rest of his text. The 2 elements are the continuous spectrum, described by Newton but in question until upheld by Helmholtz against Brewster, and the idea that the mixing of paints is, quote, governed by the rules of subtraction. Itten's account of the spectrum makes it clear that he did not consider spectral green to be a physical mixture of yellow and blue rays, as Brewster and Goethe had supposed. But if the mixing of paints is subtractive, and a green mixture of yellow and blue paints, like other green materials, reflects only uncompounded green wavelengths, how then does green equal yellow plus blue? The only reconciliation I can think of is that Itten harboured the 19th century idea that colour vision involves cells tuned to receive red, yellow and blue wavelengths, and that green wavelengths stimulate the yellow and blue receptors to create a mixed sensation of green, as Josef Albers would offer as part of a, quote, plausible explanation for afterimages in Interaction of Colour in 1963. The obvious unorthodoxy of this view may be the motivation for Itten's statement that how we discriminate these light waves is not yet well understood. Much more commonly, however, traditional colour theory seems to simply reside in quarantine in the minds of its adherents, alongside completely incompatible scientific ideas about light and colour. The other problem is how can primary red paints, if these pass on only the red rays of the spectrum, subtractively generate full colour mixtures with paints extending around 2/3 of the colour wheel. In terms of modern colour theory, they can only make high chroma mixtures with paints as far away as the nearest subtractive primaries, yellow and magenta, which share their very high reflectance of red wavelengths. Inevitably, paints of Itten's primary red hue make very high chroma mixtures with his primary yellow, but only very low chroma mixtures with his primary blue, as shown in my rather sacrilegious diagram B. Primary blue and primary yellow are essentially opposite in terms of light mixing and opponency, but, as we've seen, the former nevertheless reflect enough green wavelengths to cause mixing paths with yellow paints, all of which reflect large amounts of green wavelengths, to curve outwards through medium chroma green. The impossibility of mixing purples above a very low chroma from perceptually pure red and blue is a very well-known problem with trying to use a palette of the traditional primaries in practice. A practical workaround that dates back at least to the end of the 19th century is the double or split primaries palette, consisting of a warm and a cool version of each historical primary. The revival of traditional colour theory in the 1970s was almost inevitably followed by the revival of this double primary strategy, most famously in the best-selling book Blue and Yellow Don't Make Green by Michael Wilcox in 1987. Wilcox attached to the traditional double primary strategy a new formulation of traditional colour theory that incorporates a model of subtractive mixing without the subtractive primaries. In Wilcox's 1987 formulation, the wavelengths said to be passed on by a paint correspond directly to its colour, so that, for example, a lemon yellow paint is said to reflect a large amount of the yellow band of the spectrum and a small component or impurity from the green. Colour mixing of two paints is said to require having a quantity of this secondary colour, impurity or bias in common. Thus, while in Itten's colour theory we get orange from mixing red and yellow paints because yellow plus red equals orange, in Wilcox's theory the red and yellow components neutralise each other and the mixture reflects just the orange wavelengths that the paints have in common. In modern colour theory, all yellow paints reflect most of the red, orange, yellow and green parts of the spectrum, so that a subtractive mixture with a red paint reflects a large component of red wavelengths and a small component of wavelengths through to green, which combine additively to make orange light, much as they do in a single pigment orange paint. While each explanation works in the context of its assumptions, only modern colour theory can account for the particular effectiveness of one impure blue, cyan, one impure red, magenta, and one yellow paint in mixing an exceptionally large gamut of colours. Figure A compares the gamut of the traditional primaries. A double primaries palette works in practice primarily because it includes true subtractive primaries as the three so-called cool primaries. The three warm primaries are very high chroma pigments that extend the range of mixtures beyond the subtractive primary gamut into reds to orange yellows and blues. Traditional colour theory refers to a scale of value or tone as well as to the colour wheel, but these dimensions are generally either treated in isolation or integrated only superficially. As a three-dimensional framework, Itten dismissed the Ostwald system, which had been used in other classes at the Bauhaus, and ignored the Munsell system, which by that time was very widely used as a standard in art, science and industry, and reverted to a simplistic spherical model, externally like that developed by Runge in 1810. These spherical models express the way that object colours become more restricted in chroma, colour strength, as they approach black and white, but their vertical dimension is essentially meaningless in that colours of very different grayscale value, for example primary red, yellow and blue, are forced to lie at the same vertical level. The colour teaching of Josef Albers is sometimes lumped with that of Itten, but was quite different in many ways. Albers included the Ostwald and Munsell systems, favouring the latter, in his courses, ignored Itten's colour circle and sphere, and was sceptical of schemes of objective colour harmony. Albers did treat red, yellow and blue as the painter's primaries, but he also discussed the psychological and additive primaries, and his teaching can certainly not be said to be founded on the historical primaries. Unfortunately, but perhaps inevitably, his much less dogmatic and more experience-based approach ultimately had less influence on art and design curricula than Itten's formulaic and self-contained system, which in effect insulates the teacher and the student from the last century and a half of developments of our understanding of colour. The revival of traditional colour theory since the 1960s and 70s was not based on a successful challenge to the truth of modern colour theory, but must be understood in the context of the concurrent reduction and elimination of other technical elements, such as traditional drawing skills, anatomy and perspective, in art education over the same period. Traditional colour theory anachronistically maintains views of the nature of colour that prevailed before the late 19th century Helmholtz Maxwell Hering revolution, and its relationship, or lack of relationship, to modern colour theory is in some ways like that of so-called creation science to modern biology. The difference is not between science and art, but between the sciences of different eras. Perhaps its most unfortunate effect is that students can become adapted to simplistic treatments of colour, making modern colour theory seem unnecessarily complicated when it's first encountered. If 90% of books treated anatomy or perspective in an extremely simplified way, you'd get a similar shock the first time you saw some real and artistic anatomy or perspective. Art and design teachers educated in the age of Itten now occupy positions of authority and influence, and it is understandable that many of them are not planning to give up their attachment to simplistic traditional colour theory anytime soon. Nevertheless, there are encouraging signs that some teachers are beginning to question the ethics of presenting colour theory that is a century and a half out of date and entirely incompatible with their students' digital studies. Probably the most powerful force for change will come from students, who pay a lot for their education these days, and in many institutions have considerable power to penalise outdated teaching through student feedback surveys. The current situation among art teachers is especially disappointing when we recall that a century ago it was not a scientist but an artist and art teacher who published the system that would become a cornerstone of modern colour theory.